Okay, I think we're going to get started. So hello, everyone. Thank you for coming and joining us tonight. My name is Elizabeth Ponce. I'm the Public Programs Coordinator for the LIST Visual Arts Center. And we're so excited to be participating in Cambridge Science Festival this year and to be bringing you a really special program tonight. So as you may have noticed walking into the building, the LIST has a new eye-catching piece of public art right outside in the Kendall Square open space, The End of Signature. It's a two-piece light sculpture by the artist Agnieszka Kurant, and it now illuminates the plaza. So Kurant developed this public artwork in collaboration with a group from the MIT Computer Science and Artificial Intelligence Lab, otherwise known as CSAIL, Professor John Guttag and his doctoral students Katie Lewis, Divya, Shanmugam, and Javier Gonzalez Ortiz helped to inform and realize this piece of public artwork. So tonight they'll be sharing their work with us. And so please welcome two members of the CSAIL team, Divya and Javier.
Hello everyone, so I'm Jose, and I'm here with Divya, and we're going to be speaking about the End of Signature project and kind of all the different kind of the. Can I just leave it? No? Okay. And kind of a lot of what the development of the artist involved, as it's kind of like the collaboration between kind of the artist and the computer scientist. So first, here's the team, and kind of I was lucky enough that a lot of the introductions already made for me, but kind of the artist, Agnieszka Kurant, has done a lot of kind of conceptual art and was kind of commissioned a couple of pieces for the Kendall Square here, and reached out to John, who's really interested in this, and then we worked and collaborated with her developing these pieces. And in order to understand this project, we need to kind of look at the both kind of parts that intersect in this project, which are kind of the conceptual art angle and the AI-generated art. So kind of that's going to be what the structure of the talk looks like. We're first going to be looking at the kind of the recent progress and kind of the different techniques for AI-generated art, and then we're going to be studying kind of what the conception and the meaning of the piece is and how the development process came about. So kind of computer-generated graphics are nothing new. Like they have like a fairly long history of like several decades where kind of practitioners have been getting better and better. Like this kind of VFX professionals have getting more and more photorealistic images generated by computers. And two kind of prime examples of this are kind of all the stunning kind of CGI and VFX that we can see in movies. And kind of more recently, we can see like all the progress that is being made for kind of video games. We're getting like very, very realistic scenes. But in both of these scenarios, this is a really manual process. There's like thousands or like tens of thousands of human hours devoted to kind of tweaking and laboriously creating these environments. And what we're after is, instead of that very kind of manual and like rule-based process, looking at how AI will kind of create graphics. And AI has been breaking the news kind of more and more in the recent years, mostly because it's been able to solve problems that kind of were, and we didn't have any good solutions for. So for example, researchers were able to figure out how to build like an AI system that could be the world champion at Go, which is like a notoriously hard game. And AI has also been able to solve kind of the long-lasting problem of how to do protein folding. In both cases, we now have systems that can solve this, but we did not kind of explicitly tell the program what the logic of the operations are. And that's because they are kind of systems based on AI. And a lot of the time when people are thinking AI, kind of the underlying kind of technology and discipline is what's often called machine learning. Machine learning, it's a huge kind of area of study that involves a lot of different disciplines in science. And it's really hard to kind of neatly summarize, but I'm still going to try. And the way I see machine learning is that instead of just having a program that has a bunch of instructions, it's a combination of having data and having algorithms that try to understand the data. And kind of the key aspect here is having data that you're kind of trying to understand. And in order to illustrate this with an example, say for example, we have a really large data set of human faces because we're interested in kind of modeling human faces. And the first thing is collecting the data set. You need like a really large data set, and kind of a golden rule in AI is the more data you have, the easier it is to kind of train a model. And what we do is we get all of this data, we feed it into a machine learning system, and kind of it optimizes for a while. And what it's trying to do is trying to kind of understand like all the different properties of the data, so then it can use them. And the output is that if we have data of good enough quality and a model that can kind of understand that data, we're now able to kind of generate new data that is completely imagined. Like these people on the right are not real people. They are very convincing looking images, but they're completely made up. And they don't correspond to any of the people that were in the training data set. So with this, people figure out like with good enough quality data sets, you can get with kind of AI algorithms, and faces was one of the things that kind of AI got really good at. And now we've seen kind of things like probably seeing a lot of applications that can do a lot of really complex transformations in faces that previously they weren't impossible. Like people with a lot of skill in Photoshop could kind of slowly and kind of laboriously create these images. But now kind of we can get them pretty much instantly thanks to kind of how AI understands the human face. And similarly, kind of even more complex transformations, like how you go from an image to like a portrait of a person, and how kind of you transform that photo into an older version of that. There's a lot of complex edits that, again, like maybe with enough expertise, enough kind of hours of work, a Photoshop magician could pull off, but now we can get that nearly instantly, and the AI understands the wrinkles, understands the white hair, understands all these small details that we kind of use to be sure that this is a convincing looking image. The limitation then is that kind of the data kind of conditions the model. Like if I now want to generate images of cats, I cannot use the previous model. I need now a new model, and I need critically a new data set that needs to contain a lot of kind of faces of cats. But if I have that data, it just goes into the algorithm, and sure enough, the algorithm will get really, really good at generating completely made up cats that are extremely convincing, and that you will have like a really hard time telling apart from real photographs. However, this is still kind of natural images. This is not art, but kind of the same rule applies. If you have a kind of high quality data set that contains a lot of art, and you have a model that can optimize for it, then what we have here, like with enough examples, we now can create completely new synthetic art from the distribution. And it was really impressive, but of course there's kind of one kind of issue, right? That the AI isn't really being creative, right? It's not kind of creating like new art. It's just like copying and trying to understand all the data that it has seen. Like ideally, we want kind of AI that kind of understands concepts and can create kind of these new concepts. Well, that was pretty much what happened in the past year. Like a new kind of family of models came about, and these models, instead of having this set of images to now new images, they looked at the problem slightly differently, and what they were able to pull out is kind of given a description of the image, then now create the image. So now we're still going to need a lot of examples of like what the description of an image is and that given image. But if you have enough of them, and the internet is full of examples of images with captions, then we can train one of these models. And critically, we can ask asked it for things that it have never seen before. And this was probably the most surprising aspect for a lot of people, that now AI was kind of like interpolating and creating completely new concepts, right? Like a photo of like a confused grizzly bear in a calculus class, or like this really convincing like cat bunny hybrid, or completely impossible things like a medieval painting of the Wi-Fi not working. And while there are still like small artifacts here and there, it's kind of important to understand that this is like an early iteration of these models. They're only going to get better over the next kind of months, or years, or even months. And not only the AI is understanding simple kind of concepts like animals and like places like glass, it has like a really wide range of styles and kind of personas. Like here, for example, we can see that understands what kind of stained glass is and how to put a skateboard in a stained glass, even probably not that many stained glasses with skateboards. You can see that it's familiar with what Batman is. Batman is kind of like a pop culture reference. It was enough times in the data set to appear here. And it also understands about artists. Like here we're asking about like the style of Jackson Pollock, and it kind of, to the best of its ability, is able to transmit that here. And lastly, we can see that like the pop culture understanding goes really far, where like it can even understand the specific movies here. Where like we're asking kind of to put like Kermit the Frog, which is a Muppet, into Blade Runner, which is like a cyberpunk dystopia, and it's able to kind of make a really convincing Kermit the Frog in that scenario. The model is definitely not perfect. It has like some kind of weird kind of shortcomings. Like these AIs are still struggle with text. So for example, we have here like a promotional image introducing the new McSushi, which is not a real menu item from McDonald's. And you can see that all these images, which correspond to that prompt, are very, very convincing, right? Like they all have something that looks like sushi. They all have like all the kind of marketing and publicity details. But then when you start paying attention to that really convincing kind of font, so like the graphic design looks right, but the text is completely nonsensical. Like the M of McDonald's is correct, but anything else, you cannot make sense of it. And following kind of this kind of text to image API, but like interface, people figure out that it was actually easy to exploit like a modified version where maybe you know what you want, but you also might have like a clear kind of notion of what the structure of the image should look like. Like, right, maybe you know kind of, you can sketch how that image looks like, and you can actually combine that and give like an image and a piece of text as the AI, and the AI will kind of take that into account, kind of sort of like a prior knowledge of how everything should look like, and generate like this really convincing futuristic dome city. And funnily enough, people have shown that this can go really far with kind of using their kids' drawings as inputs. And even if it's really low detail and like only like a bunch of pencil scribbles, the AI can make sense of that and generate like a very kind of convincing photorealistic image. Another one of these shortcomings is maybe the AI knows what Batman looks like, because Batman is extremely popular. It's like so much merchandise and movies. But it probably doesn't know what I look like, right? There's now kind of a challenge of like, how do I describe myself to the model? Like I can try adding a bunch of adjectives, but it's going to be really hard to convey kind of my face and like a lot of those details to the model. Well, people actually figure out that like a kind of like a early way of doing this. And what you can do is just kind of add a new kind of word to the AI vocabulary. And once you have that kind of word in there, you can combine it with kind of everything you want, like a picture cartoon style, or like different caricatures in like a Funko Pop. And what you just need, like here, there's nothing crazy. You need some know-how, but this was trained on just like 25 images I took this morning. It was nothing like, it's not like a deepfake where you need like thousands of images. So now, given all these kind of doomsday revelations of what like AI is doing in the art space, is this kind of the end game? Well, no, not really. Like what I've been showing so far, has a lot of cherry picking, which it happens, and a lot of the examples that you might see online, a lot of these models are definitely cherry picked. But the good news is there are actually cherries to be picked. Kind of for a long while we could not even do that. And an example of how happens is maybe I just give this really simple prompt of a river running past a cozy cabin in the mountainside. And a lot of these images look really good, have a lot of kind of details, have like this kind of Bob Rossi look. But if you actually look at the semantics, they are wrong. Like the first one doesn't have a cabin. And the second one, the cabin is in the middle of the river, which makes no sense. And the last one actually looks good. And that one was probably the one that you will send to your friend, like not the other ones. You kind of discard those. And even if you get good examples, so you kind of get better, there's kind of like a lot of language of how to do it, there's still kind of like a missing piece, which is that the human has to lead kind of the artistic vision. There's a lot of kind of trial and error of how to get things right. And I think one of the best examples was someone that wanted to generate kind of this logo of an octopus handling boxes for their kind of database. And they tried to use one of these balls, and they kind of recorded everything in a blog post, and kind of all the different iterations where they were trying different prompts, different styles, different modifiers, and slowly but surely they were kind of getting closer to what they had in mind. But it really made clear that it was like a new tool that needed to be kind of mastered, and that a lot of the kind of trial and error needing to master a new skill was still kind of definitely there. And in the right hands, people are kind of, even if it's really early, showing that it has a lot of potential. So here, what someone online managed to do is hook Photoshop into one of these. It's in one of these tools, and what they're doing is they're constantly prompting the model for different sections with slightly different prompts, kind of keeping the same style and doing different regions. And while this has a kind of like a skill that is required of kind of understanding how to use Photoshop and how to manage them all, one of the main things to note is you still need like the kind of the artistic knowledge of how to make this really complex composition. It's definitely the case that this tool will kind of probably remove a lot of hours of like really intricate drawing that like now you can make like concept arts much faster. But it's not just going to replace artists. It definitely feels like another kind of tool that can be in their toolbox. I think this runs for slightly longer. But like here, for example, we can see that people add like a lot of like style modifiers. So here, kind of they put like Ghibli style, they put like hand drawn. They're kind of filling in a lot of in order to kind of prime the model for specific colors. They also kind of say like, oh, I want a specific structure here. And again, this is someone that just like hacked this, but it will kind of in the next coming months, probably a lot of tools will start integrating and things like that. So while it won't replace artists, or it doesn't seem the case yet, there definitely raises some important ethical questions, right? Like now people are realizing that really artists that the model understands really well, like for example, Van Gogh, like now you can generate like fairly easily like thousands or like tens of thousands of really convincingly looking Van Gogh paintings. Now we start flooding the kind of the internet or like our shared kind of media space with a lot of these images that kind of dilutes the original artist's work, and like we might not even know at some point like what really is like a Van Gogh painting. And while this seems far-fetched, this is actually already happening. There is this really famous digital artist called Greg Rukowski that has done a lot of highly detailed digital art in a lot of like fantasy settings, and people figured out early that adding kind of by Grey-Rukowski to the prompt will just give like images that will be more detailed, that will have like a lot of the properties. And now the artist is complaining that like, will he able to find his own art between like all this AI generated art that looks like his? And even there are also issues about like what the copyright about like these models are. Like the models have been trained in a lot of copyrighted material, and they sometimes can regurgitate that. So here on the right, we have that with the right prompt, the model is just kind of creating some kind of nightmarish looking stock photo. And on the kind of bottom left, or like the middle right, we can see that it has generated like a slightly blurry and a bit broken Getty Images watermark. And that was because the model has seen like probably thousands of watermark Getty images. Those are whose copyright corresponds to Getty Images, which people are under the suspicion that is going to sue or something one of these models for using their copyrighted materials. So this raises a lot of questions of kind of how these really large models that have seen lots of our work and like how the kind of the ethical implications of this. And this is actually at the core of like the artwork that we're here presenting. And I'm now going to hand it to Divya that is going to explain the collective signatures in Kendall Square.
Cool, thank you. So as Jose said, end of signature addresses these topics of collaboration and authorship and what that can look like in the future. So in the next few slides, what we hope to do is give you a sense of the process behind coming up with these signatures, some of the technical details, and what it was like to work with Agnieszka. So the end of signature consists of 2 signatures. The first is a Cambridge signature, which hangs on the building that we are in today. And it represents the Cambridge community. I think that you can find my name in it if you wanted to. But it's a blue LED sign that flickers once every about 60 seconds. So if you stand there for long enough, you'll see it flicker. The second signature that's a part of the end of signature is the MIT signature, which signs and re-signs itself every once in a while. And the motivating idea behind these sculptures was, in Paul Ha's words, to illuminate a new campus gateway and inaugurate a space of exchange between MIT and Cambridge. And the idea was to do this using these collective signatures, one for Cambridge and one for MIT. So what is a collective signature? The collective signature, it's inspired by this idea of collective intelligence, or this idea that there's wisdom in crowds and people can build really amazing things when they work together. So examples of this are things like social movements, or like things like Black Lives Matter, or scientific innovations, which you see around MIT. And the idea of the collective signature comes from the fact that these works in art and science are often credited to a single person or a lone genius. And collective signatures hope to credit the community as opposed to the individual. So the idea of a collective signature is a running thread through Agnieszka Kurant's work, who's pictured here on the left of the slide. She was born in Poland, and she lives in New York City, and her work often deals in systems, sculpture, and film, and has been exhibited across the world. She operates at the intersection of art, science, philosophy, and technology, and I encourage you to browse her work, her other work, if you have time, because it's really fascinating and deals with a lot of these topics that Jose talked about. But something that's kind of shared between her pieces is that she analyzes communities as something like a superorganism or as sum of its parts. And she analyzes them as these like persons with personality traits and develops these collective signatures to represent them. So on the right of the slide, you see one of her installations at the Guggenheim in 2015, which was made from signatures solicited from museum visitors, from people in the art world, from the community, like the surrounding community, and kind of follows her vision of communities as superorganisms. And in her words, the idea behind these sculptures is to get at the way that handwriting in maybe 10 or 20 years may be a relic of the past. When in today's day, like we often like scribble our signature on a touchpad and things that way. And in her own words, the end of signature is about the end of handwriting and how that expired at the same time as the idea of a single author. So here's another one of her pieces, which was installed at the Cleveland Museum of Art in 2018. And this signature was created from custodial staff, gallerists, museum visitors, and curators. So what Agnieszka asked was, what if we used AI and some of the advances that Jose talked about to create a signature? And so she got in touch with John, our advisor, and we got to work. So as with many machine learning models, the process began with data collection. So the List Center collected signatures from both the MIT community and the Cambridge community by distributing the form that you see on the right of this slide, which basically says, sign here in this box if you want to be a part of public artwork in Kendall Square. And at the end of this process, we got 600 MIT signatures and 300 Cambridge signatures. There were definitely some outliers in the data set. There's one person who signed with something that looks like an alligator in a hat. But for the most part, a lot of these signatures looked like normal, signatures. So this kind of started the part of the process that me, Katie, and Jose were the most involved with, which is how do you go from this data set of signatures to something that represents all of those parts? So one thing you might do is just take the average of all the signatures that we had submitted. And you might end up with something that looks like this, which basically shows you in the light parts are places where people typically sign, and in the dark parts are places where people don't really place their signature. But you can really only tell two things from this image. First, that people usually sign in the center of a box. And second, that signatures are a little bit taller towards the left compared to the right. So overall, this wouldn't make a very pretty sculpture. And on top of that, it doesn't have many of the features that we know are parts of a signature, like identifiable letters or anything like that. So instead, what we decided to do was use generative adversarial networks, or GANs, is what I'll call them for the rest of the presentation. So GANs consist of two models. The first is the generator, which attempts to generate realistic images, and the second is the discriminator, which attempts to say, is this a real image or not? So to illustrate this, we'll go through one example. So let's say we're trying to build a GAN that generates images of cats. So what we would do is we put a random number through the generator, and it tries its best, and it comes up with this image of a camel. It would then hand it off to the discriminator, which would then say, obviously, that is not a real cat. And so then the generator would go back to the drawing board, try and improve its own conception of what a cat is, and maybe it would come back with this image of a tiger. It would then hand that to the discriminator, but in this time, the discriminator has also improved. And so it says, still not a real cat. So the generator improves and improves, and it comes up with something that looks like this. So on the left, you see something that does kind of look like a cat, but on the right, you see this creature with multiple eyes, multiple ears, definitely looks like a synthetic abnormality. And it gives it to the discriminator, which says elements of a cat, but still not quite. And finally, at the end of this process, what happens is the generator is able to create an image of a cat that's kind of convincing. In fact, I don't think I would be able to tell that this is not a real cat. And it hands it to the discriminator, which says that's definitely a cat. But the truth is that this image is totally synthetic and not a part of the data set, not a cat that exists. So this is kind of the idea behind GANs, that both of these models help each other improve, where the generator becomes better at producing an image that can fool the discriminator, and the discriminator becomes better at distinguishing real images from fake ones. So in the context of our project, what we try to do is create a generator that generates realistic-looking signatures, and the discriminator tries to tell if this is a real signature or not. So this is just one step in the machine learning pipeline that we used. So in this first step, we train a GAN to create these synthetic signatures, something that might look like that black and white image to the right of the first gray box. And we take that set of raw generated images, and then we post-process them using Bezier curves. And what Bezier curves are, they allow you to select points and produce a smooth, natural-looking line through those points, and basically create something that's more easily translated into a sculpture. And so what we would do is we would take those raw images and the post-processed images and hand those off to Agnieszka to get her feedback on how this might depart or adhere to her conceptual vision. And she would get back to us in the form of emails, drawings, and conversations to communicate what exactly she wanted the model to produce. So here what you can see is an early version of the MIT signature where she's kind of illustrated some of the forms that she was imagining. And finally, I would say that this was the hardest step of the process. We had to take that feedback and translate it into changes to the machine learning pipeline. So we had to go back and say, oh, maybe we need to resize the images to achieve this aspect ratio, or clean the data in this way to get more crisp lines in the generated images, or choose our anchor points differently in the Bezier curve step. And we would take all that feedback, translate it into technical terms, and then repeat this process. And we went through this iteratively multiple times. So in the next couple of slides, I want to show you some of those iterations and what the signatures looked like in those steps. So here is the first batch of signatures we sent to the artist, which is kind of impressive. They do kind of look like signatures. And in response, Agnieszka got back to us to say, you know, what I think would evoke more of a human signature is something that's wider. Something that spans more of the page and has more kind of individual parts to it horizontally. And so this kind of directly informed how we, pre-processed the signatures that we had collected originally to produce more horizontal forms. This was another batch of signatures that we sent to her, and in response to these, Agnieszka indicated, these are simpler lines with fewer loops and curves, and so what would be great if we had like a bit more of a complex line with a little bit more detail, which directly informs the anchor points that we choose in translating that raw image to, the Bezier curve post-processed image. So you can tell these are getting kind of like closer to what the signature sculptures look like. So we sent these over to her, and she mentioned, that it would be great if we had longer elements protruding upwards and downwards. And I thought this step was quite interesting because it's an instance where she was incorporating her aesthetic vision into the images that we were generating, and some of the manufacturing constraints that we had to deal with too. After multiple iterations, many of which are not described by these slides, we ended up with these two signatures, the left being the Cambridge signature and the right being the MIT signature. We produced these different signatures by training different models. So the left signature is produced by a model that was trained on the Cambridge signatures, and the MIT signature was produced by a model trained on the MIT signatures. So over the course of this process, Jose, Katie, and I had a number of takeaways about this process of collaboration between human and AI models. The first is, as Jose said, there's large variation in sample quality. For every good image of a signature, there are 10 bad images of signatures, and images that we couldn't translate into a sculpture. So it is impressive that these models are able to generate these realistic images, but it's definitely not consistent that every image is usable. The second thing is that this process was inherently iterative, and multiple rounds of feedback were necessary to achieve the final form. And we saw our role mainly as bridging the conceptual vision that Agnieszka had with the technical possibilities of GANs. The final thing is that models have no real notions of concept. So you and I understand what a signature looks like, the fact that it's cursive-like, it has these thin black lines, but models have to learn that directly from data, and embedding that into a model is actually quite difficult, especially with the number of samples that we had. Some of the models that Jose talked about operate with data sets on the scale of millions of images, and we had fewer than 1,000. So reflecting on this process, we started it in 2019, and many of the things that Jose talked about have happened, in the past year. And so much has changed with image generation models as they continue to improve and generate more and more realistic images. So if we were to start this project today, maybe we would use one of these text-to-image models that Jose talked about. There's one called DALL-E, and we might prompt it with something saying, a signature representing all of mankind. And these are some samples that we got in response to that prompt. So some of these images could be transformed into a sculpture. The left image is kind of a nonsense word, and the middle image is something that looks a little bit like Arabic script. But you can see in the right image, the model has interpreted the phrase to mean multiple people signing documents at the same time. So there's a long way to go to bridge the gap between concepts and machine-generated images. I think on top of that, DALL-E hasn't been trained on one community's signature. So I think there's conceptual value in adhering to a particular vision across a machine learning pipeline and making sure that those steps reflect your message. So in sum, our collaboration shows that machine learning represents a powerful tool for artists to use to execute visions about the role of technology in our future. And I think we're about to see a new chapter in the relationship between art and technology. And if our project is any example, artists have a huge role to play in guiding these collaborations. Thank you. And thank you to the LIST, too, for giving us this opportunity to participate in this project. At this QR code, you can find a report on the collaboration, and feel free to come talk to us afterwards. We'll be here for the Q&A, too. Thanks.